Hello, my name is Zohra Shaghan and I'm going to explain project number 2. First, I would like to remind you about the first project that I did, Chameleon Office. So where I mapped the triangle openings on the surface in that project. The openings were controlled within an arbitrary attractor point at a time within a 3 by 3 hexagon models, and this was the result. In this project, however, the openings are controlled based on the sun vector. So first of all, I had to simplify the project. So first of all, I only considered the hexagon, the simple hexagon this time, and ignored the triangles. And the second is that in order to have various opening, the cells are mapped on a circular surface. So the normal vector and the sun vector makes different angle for each cell each time, which cause different openings. So I would like to explain sun path briefly. So with this ladybug component, you can get sun path easily. So you just need to feed this node with the EPW file. For example, I feed it with the call station EPW file, and then you get different output like dry bulb temperature, location, and global horizontal radiation, which are used for this node of sun path. So you just need to feed this, for example, with 24 hours and, for example, 12 months to get this beautiful sun path of the year. And the results are shown here. For example, I get two sun paths because I choose both a dry bulb temperature and the radiation. And the important thing is that you can also get this line, which actually is the vector, the sun vectors between your project and the sun. So for my project, I just only needed to calculate only one sun vector because I wanted to adjust my openings based on sun vector, and then those sun vector could change each time. So I imagined 3 p.m. 8th of the May for this project, but however the time can be changed with the slider and cause different pattern each time. Okay, so this is the scripted code of Python. I used launchbox to create this hexagon on the surface. Then I used the base surface, the points, which is the center of the hexagon, and also the sun vector as an input. And then I made a for loop through these inputs. Then I, as a result output, I get the normals of each point on the hexagon on the surface, and the other output actually is the dot product between the sun vector and also all normals of the hexagon. So basically, because both of them are unitized, so basically the dot product is cosine of theta. So this list of numbers, I just needed to remap them and use them for scaling and moving. So I remapped them in order to get rid of the negative number. So this is the Python script for the scale, and then I moved all those scaled hexagon, and then I lumped them all together to get this opening. So the movement actually again used the remap numbers. However, this time I used the reverse numbers of the remap for the movement. They had to move according to the align with their normals. So as you see, the result is that the thickness different in each location. So if the angle is small, the angle between the normal and the sun vector, so the thickness is bigger, and if the angle is bigger, then the thickness is smaller. So the scale and movement has somehow a reverse relationship with each other, and this is the result. The last part is the Galapagos part. So in the Galapagos part, it includes two sections. One of them is the genome, and the other one is the fitness function. So for the fitness function, I use this node, the radiation analysis. So the radiation analysis node actually is to calculate the radiation energy on a certain surface in a year. So the input I use is the base surface plan because I wanted to calculate the radiation on this base surface, and then I use the lofted objects that I get it from this part in the genome that will be changed each time through the scale factor. I used it as an input for this node, this radiation node, as a blocker, actually as a shading. Then I get this set of number. So these setup number are actually radiation number. So each time that the scale factor change, a new set of openings will be generated and will be given as an input to the radiation analysis component, and the component will generate new set of values. So based on the grid size each time, the radiation results gives 1275 values, which demonstrate the radiation energy in kilowatt hours per square meter, and it is yearly, and which demonstrate the solar radiation on ellipse plan. So it's worthwhile to mention that the amount of the desired radiation energy depends on the design intention and also other parameters in terms of heating and cooling. However, in this example, an arbitrary range of 50 to 80 kilowatt hour per square meter is chosen to only test the Galapagos actually. So this is the for loop. This is the fitness function, and the goal is to achieve the maximum number of values of the radiation in this specific range that I defined for the ground floor plan of the ellipse. So I just wrote a simple conditional if statement. And the second part is the genome part. I used the scaled cell that I already had got from the last part, and these are the scale cells, and I used it as again to rescale them, and this time the scale factor is this slider number that can be changed and can be used as a genome. This scale factor changes and then give me the result of a new scale. That this new scale can be lofted. The geometry can be lofted with the original hexagon, and this lofted, as I said before, will be given as a shading to the fitness function. So I ran the Galapagos, and it took about 3 hours. Then I had to stop it, but it gives around the scale factor of 0.894. It gives about 183 numbers, which was the maximum numbers. It starts with 109, and then at the end it gives 183 numbers for the maximum numbers of the value. Thank you so much. Hope you enjoyed.